Welcome back to another lecture. So in this lecture, we're going to go through intermolecular forces, and we start with dipole-dipole interaction, and then hydrogen bonding, and the last one, it will be the dispersion force. Okay. So technically, we are dealing with van der Waals forces, and we can classify them as dipole-dipole interaction, hydrogen bonding, and also dispersion force, or sometimes we say London forces. Okay, and I'm going to go with the first one, which is dipole-dipole interaction. How do we get dipole-dipole interaction? And so the dipole-dipole interaction, it comes from permanent positive and negative charges on the molecules. So that means you are dealing with polar molecules. So in order to have dipole-dipole interaction, we need to have mu to be bigger than 0. That means our molecules are going to be polar. Okay, and here we have permanent. Okay, I keep saying this one. We have permanent positive and negative charges. Okay, so we have permanent positive and negative charges. And that's the reason we get technically interaction between the molecules. Okay, so we can draw it this way. So I'm going to say from now, whenever we talk about electronegativity, which is the ability of pulling bonding electrons to yourself, okay, to the right side of the periodic table, increases, down in any group decreases. So I'm going to say increases to the right side of the periodic table, down in any group decreases. Okay, again, reminder, electronegativity of fluorine is going to be higher than electronegativity of oxygen, and that's higher than electronegativity of nitrogen. Okay, because we are shifting to the right side of the periodic table. Next, electronegativity of fluorine higher than electronegativity of chlorine, and that's higher than electronegativity of bromine. Okay, because down in any group, electronegativity decreases. That's one. Okay, and we talked about hybrid orbitals. So we said, okay, sp has 50% s character and 50% p character. Okay, next, and sp2, we said this is going to be 33% s and 67% p character. And then you go sp3, okay, it will be 25% s character, and next one it will be 75% p character. Okay, as s character goes down, okay, or as the contribution of s character goes down, electronegativity will go down. Okay, again, as the s character goes down, electronegativity will go down. So between here, like for example, between these two carbons, so I'm going to say between these three carbons, we have a carbon attached to another species with through a triple bond. Okay, say we have this one. Okay, in that case, we call the hybridization of this carbon sp3, sp, my bad, sp. Next, we have carbon attached to another carbon through a double bond. Carbon has sp2, sp2 hybridization, and the last one, say carbon attached to another carbon, and each carbon, it has 3 hydrogens, and the hybridization is going to be sp3. Okay, so the hybridization for this carbon, it will be sp3. Okay, which one of this is more electronegative? Okay, which one of this is more electronegative? Okay, and or which one has higher tendency to pull the electrons to itself? The one with sp hybridization. So I'm going to say first one, it will have higher tendency to pull the electrons. Okay, so if you have that carbon somewhere, okay, attached to another species, that carbon is going to pull electrons stronger to itself. So I'm going to say electronegativity has this actually trend. Okay, next. So we're going to attach carbon to oxygen, and we have three here, two carbons, and each carbon, it has three hydrogens. Okay. Oxygen clearly is not active. So what do I need to do with it? Okay, you simply draw a circle around oxygen, okay, and ask yourself how far we are from 8. Right now, I see 2 electrons inside the circle. I made 2 bonds, so I'm 4 electrons shorter from 8. So I'm gonna give it 4 electrons to make it active. Here you go. 4 electrons. Now let's assign the hybridization. Hybridization for, okay, let me show also the, like the hydrogens attached to the carbon. So this one is CH3. Okay, we have carbon here, and then we have oxygen with 2 lone pairs. Okay, the first carbon, it has 4 sigma. That means hybridization for this carbon must be 1 from S, and we need 3 from P. It will be sp3. Okay, this carbon again is identical to the left one, so it will be sp3. Okay, how about this carbon? That carbon, it will be sp2. Why? Because I have 1 sigma, 2 sigma, 3, and that's a pi bond. Okay, pi bond. So we have sp2 hybridization. How about oxygen? Oxygen, you can say, is sp2. Why sp2? Because oxygen, it has 2 lone pairs, 1 sigma plus lone pair, it will be 3. So the hybridization, it will be sp2. Okay, sp2. Okay, so bond angle is going to be around 120, and I assign the hybridization for each one. Again, let me redraw this molecule. Okay. The central carbon has, because it has sp2 hybridization, is going to apply more force. Okay, it will pull the electrons to itself. It means it's going to leave a positive charge on those 2 carbon. But oxygen is the one with the highest electronegativity. So what will happen? In that case, we say oxygen is going to pull the electrons to itself. And so we will have the maximum negative charge on oxygen. Okay, and here we will have a positive charge. So all elements are trying to give electrons to technically oxygen. Oxygen is the species with the technically, or the, like the head with a negative charge. And the rest, like 2 carbons, they have a positive charge. Let's take that molecule and pair it with another molecules. So we have a carbon attached to oxygen. We just proved that there is a negative charge, CH3 here, CH3. Okay, so we said we have a negative charge. If I draw a circle technically around this, I have a negative charge. The negative charge mainly is located in this position. And there we have positive charges. Okay, if you copy paste another molecule around it, okay, the second molecule, it will reach it in a way so that the positive charge will be pointing to oxygen. Okay, so the positive charge, okay, let me change the color also for this one. Okay, positive charge, okay, is pointing to oxygen. Now we have two species with opposite charges close to each other. And I expect to see in like attractive interaction between them. And that attractive force, we call it dipole-dipole interaction. Why? Because we have permanent positive and negative charges. So the new interaction that we get between them, that one we call it dipole-dipole interaction. Dipole-dipole interaction heavily subject to mu. Okay. Subject to mu, because if you then have a positive or negative charges and they are not big enough, you're not going to have enough interaction. Remember, you're talking about electrostatic force. Electrostatic force is equal to K multiply Q1, Q2 divided by square of the distance between them. So what's a Q1 and Q2? Q1, you can say the negative charge, and Q2, it will be the positive charge. And what's the R? The distance between them. So if Q1 and Q2 go up, their value go up. In that case, their values go up. In that case, we say the force will go up. That means the dipole will be stronger. That one will be stronger. Okay, so the dipole interaction comes from permanent positive negative charges. Okay, in order to have permanent positive negative charges, we need to have difference in electronegativity or difference in hybridization. Okay, this is sp3, sp2, and that one is sp2. Okay, of course, that carbon also is going to be sp3. Clearly, we have different and hybridization, and that's the reason we have a permanent positive negative charges. Okay, let's go through this example. Okay, in this case, we have carbons that they are sp3, sp3. This one is sp2, and that one is sp2. Okay, how about here? Here we have sp3, that's sp2, and sp2. Okay, let's highlight these elements. Okay, so it looks these two species, they are the same, or they are sharing same components at the bottom. Okay, so the difference comes from O2 versus CH2. Okay, O2 does have sp2 hybridization like CH2, but O2 is more electronegative. Or sorry, I keep saying O2. Oxygen is more electronegative than carbon. Okay, than a carbon. Remember, you were talking about again the same hybridization. So I'm going to say because electronegativity of oxygen is way higher than electronegativity of carbon, I expect to see more here pooling effect from oxygen. So that means the negative charge here on oxygen will be more significant than this negative charge. Let's call this one, for example, 1, and call that one 2. Okay, so I'm going to say delta minus here, delta minus delta 1, okay, is way bigger than delta 2. Okay, and the output of it, the molecule on the right side, okay, or acetone, will have higher attraction force or intermolecular force. Okay, the output of this, if you have a stronger intermolecular force, okay, you will be attached to your neighbor. And if I want to evaporate that molecule to the gas phase, I need to chop that intermolecular force. It's going to cost me more energy to cut the intermolecular force. That means I'm gonna wait longer until I melt it or boil it. So let's write it this way. As intermolecular force goes up. Okay, as intermolecular force goes up. Okay, delta H for, okay, say delta H for, let me write another one. Okay, go H2, or let's say we have this. We go O, for example, F2. This is solid. We want to turn it to OF2. I go liquid. Okay, delta H of melting which is equal to delta H of fusion, will go up. Okay, that one will go up. And if you compare it also, like if you look for delta H of, okay, delta H of vaporization, I'm gonna say delta H of vaporization strongly or directly subject to intermolecular force. So the example that we had, okay, if I go back here, because the molecule on the right side, acetone, it has a higher intermolecular force, boiling temperature for it will be higher. Okay, and as you see, the boiling temperature for an isobutylene is around -7 degrees Celsius, while boiling temperature of acetone is 56. Okay, so technically in room temperature is liquid. And it's true, is in room temperature is liquid, is the same compound that we use it for cleaning nail. Next force that I'm going to talk about it will be the hydrogen bonding. And what's the hydrogen bonding? Hydrogen bonding is a dipole-dipole interaction, but extreme version of dipole-dipole. What do I mean by extreme version? Okay, how do we get a strong dipole-dipole interaction? In order to get strong dipole-dipole interaction, let's go back. We said we need to have Q1 and Q2 to be big positive or negative, positive and negative charges. So anything that increase Q1 and Q2 will make the force stronger. Okay, how can I have a huge positive and negative charges on one molecule? The best way to do it, choose really electronegative element and pair it with one that has less electronegativity. But you have to be careful about one thing. You are supposed to have a bond between them. We don't want to transfer the electron completely, because if we don't transfer the electron completely, that's not going to be technically sharing anymore. That's going to be transferred. It will be ionic. Okay, let me write you an example. Okay, so if you take fluorine and pair it with hydrogen, okay, you will get this HF. Okay, still we have a chemical bond here. Okay, still we have a chemical bond between them. So there is a covalent bond between them. Clearly, fluorine is not octet. Let's give it 6 more electrons to make it octet. Now, we say fluorine is more electronegative. So fluorine will have a negative charge and hydrogen a positive charge. Now, pair fluorine with sodium. Okay. Sodium is way less electronegative, okay, than hydrogen. So what will happen? If I pair sodium with fluorine, this is going to happen. Okay. These two electrons completely will be taken by fluorine. Okay, so what do I get? I'm not going to have sharing anymore. I will have sodium with a +1 charge. So it's not delta. It's a whole positive charge. And fluorine with a -1 charge. Okay. Do I see any chemical bond between them? No. So why do I have those two species close to each other? That's the electrostatic force. We don't have a molecule anymore. So this one is an ionic compound. Okay. And whenever you have ionic compound, you're not gonna have van der Waals forces. You will have technically electrostatic interaction between two particles, ion and cations, and that's the reason that they stay together. Okay, and there is no molecule. So I'm gonna say there is no molecule. Okay, so we don't have a molecule. Okay. And when we're talking about hydrogen bonding or dipole, we want to be sure that we have a covalent bond. We want to be sure there is a chemical bond. There is a technical molecule. Okay. Now, what's the hydrogen bonding? Say you have one element, and your element is nitrogen, oxygen, or fluorine. Okay. And another one. Okay. We have element. It can be nitrogen, oxygen, or fluorine. Okay. If you take, for example, X and attach it to hydrogen, okay, like what? Like, for example, say, again, F attached to hydrogen. Okay. This one has 3 lone pairs. Okay. We will see that fluorine will pull the electrons to itself. So this is going to happen. We're going to have a negative charge here, and this one will have a positive charge. Okay, so hydrogen is a short of charge, a short of electron. Hydrogen is going to be looking for electron from somewhere else. Okay, now if you have pure HF, okay, hydrogen will be looking for another fluorine, okay, another fluorine. And that fluorine, remember, it has 3 lone pairs. Okay. And is attached to hydrogen. Fluorine has negative charge. Okay. Hydrogen has positive charge. So this hydrogen is going to try to make interaction with the lone pair of a neighbor fluorine. Okay. Neighbor fluorine, not inside. We're not talking about the one on the left. Okay, so one hydrogen from a molecule has a positive charge. It's short of electron. It will look for negative charge. Where can we find the negative charge? From another molecules. The interaction between hydrogen and one electronegative element, like a fluorine, we call it hydrogen bonding. And this is really strong dipole-dipole interaction. Is this strong dipole interaction is extreme case of the dipole interaction. Okay, why do I say extreme case? Because you have really electronegative element, oxygen, nitrogen, fluorine, oxygen. They will locate too much actual, or they pull too much electron density to themselves. So the negative charge, it will be a really big number, and also they will create a huge positive charge on hydrogen. Okay, but still you do have a covalent bond between, for example, nitrogen or hydrogen and fluorine, nitrogen and fluorine. And because still you have a chemical bond there, you can call this is intermolecular force between 2 molecules. Okay, so anytime H attached to electronegative element will get a positive charge, and it will interact with another lone pair from another molecule, and it will give you a new dipole-dipole interaction that we call it hydrogen bonding. Okay, you can change, for example, this. Okay, you can change it with, let's say, we have instead of, okay, I'm going to say instead of, for example, HF, I'm going to put water. Okay, so water has 2 hydrogen, okay, and 2 lone pairs on oxygen. Okay, clearly oxygen has negative charge, so we have a negative charge on oxygen and a positive charge on hydrogen. Okay, and lone pair, one of the lone pair of okay, forgive me, one of the lone pair of oxygen, it will interact with hydrogen, and that interaction we call it hydrogen bonding. Okay, so how do I get hydrogen bonding? Okay, how do we get hydrogen bonding? One, we need to have hydrogen attached to X. And what's the X? It has to be, okay, electronegative element like nitrogen, oxygen, and fluorine. Okay, 2, we need to have Y. Okay, and Y, it can be, okay, can be nitrogen, oxygen, again, or fluorine. Okay, we need to have a lone pair. Lone pair on Y. Okay, so that lone pair, it will interact with hydrogen, and it will give you hydrogen bonding. Okay. And this slide, as you see, we have ethanol. Ethanol, it has OH. Okay, that OH, it can create hydrogen bonding. So we have hydrogen, or it's capable of creating hydrogen bonding. And as you see, we have another molecule of ethanol, and oxygen is pointing in a way that the lone pair is closer to the neighbor hydrogen atom, and this interaction will give you hydrogen bonding. Okay. The more hydrogen bonding you have, the higher boiling temperature you will be dealing with. Or you can say this, that molecule, it will be harder to technically dissociate its component. When I say its component, two neighbor molecules, because it will be harder to dissociate them. It will be harder to boil it or to melt it. And another thing that I want to mention here, a protic versus a protic solvent. Protic is a solvent, a protic is a molecule that it has acidic H that is attached to electronegative element. Okay. And if you have H attached to electronegative element, you will have polarity. Okay. And how about protic? A protic solvent or a protic, molecule is a molecule that does not have acidic H attached to it. Okay, this molecule is polar. Mu is bigger than 0, so it's polar, but there is no H there. Okay, how about diethyl ether? Okay, that one also is polar. Mu is bigger than 0, but there is no acidic H. Okay, and that's the reason we call it a protic. Okay. Hydrogen bonding is really significant when it comes to our life. Entire of our life is subject really to like intermolecular forces, and especially hydrogen bonding. Without hydrogen bonding, we might be, start dealing with severe diseases. And structure of DNA is one of the examples that I can mention. This is really good, good subject to talk about it, and so I don't have much time left, so I'm going to pause here, and I will keep this subject for next lecture. Thank you very much, and I will see you soon.